Okay, welcome back. So I left you with this little problem about how many times fainter is basically 30 magnitude than 21st magnitude, so comparing the Hubble with ground-based telescopes. So we can deploy Pogson's relation. So let's start from that part. So m2 minus m1 is 2.5 log f1 over f2. So obviously here we're given the magnitude difference, 30 and 21, and we want to work out the ratio, really, how many times fainter. So that's, what basically it's the ratio of the fluxes that we're after here. So put in the magnitude difference, so m2 being 30, m1 being 21. And then we just need to rearrange the equation again in order to solve for f1 over f2. So let's make the log the subject first. So difference is 9 divided by 2.5 gives us 3.6. And then just need to inverse log this in order to get the answer. So f1 over f2 is 10 to the 3.6, which is around about 4,000. Okay, so effectively the Hubble Space Telescope could see 4,000 times fainter objects than the ground-based telescopes could do at the time. Okay, so that's partly because it's, well, it is because it's in space, not really because, it wasn't a very big telescope, didn't collect any more light, but because it could focus that light, as we learnt in workshop 1, into a very small concentrated region on the detector. That's really what helped let's see such faint objects. Okay, so now let's continue our story on the magnitude scale. So, like every scale in physics that you'll come across, really, or anywhere really in science, you need to sort of define a 0 point, usually somewhere along the line. You need to have some sort of absolute calibration for your scale. You could see that on the illustrative diagram that I had before. There was a 0 magnitude, okay, and that's an obvious place to sort of define perhaps how to calibrate this magnitude scale. So since the invention of the telescope, then basically a particular star was chosen that was close to, one of these, like a magnitude 0 type object. One of the very bright naked eye stars was just chosen to be a standard star. Okay, and that star is called Vega. Okay, and it's literally just defined to have magnitude 0. So that's, it's close to that, and it was defined to be that. So then every other star, its magnitude in effect is defined relative to Vega. So you see the way the magnitude system works, it's always a difference. Okay, so you've always got m2 minus m1 or other manifestations of that. Again, that's the essence of a logarithmic scale. Okay, so you're always comparing one thing with another thing. And so here you're always comparing one star with another, usually. So Vega is defined to have magnitude 0. So this means that the flux of Vega takes on a sort of particular significance. So obviously the flux here in real units, whatever they are, watts per meter squared per nanometer, perhaps, if you're working in the optical spectrum. That's often referred to then as the 0 magnitude flux. So it becomes the 0 point, if you like, the 0 point flux for that particular magnitude scale. So then, if you'll have an example of putting this interaction at the end of this lecture. Okay, so you can come back to that then, see how it works. So like I said, when you if you look up catalogs of objects and stars these days, you'll see lists of magnitudes. If you actually then want to go and turn that into watts per meter squared per nanometer, then you have to go and look up first what the 0 magnitude flux is, and then use Pogson's relation to work out that flux. So I thought I'd give you a little indication of another visual indication of the magnitude system. By showing you a sort of map of the night sky. Why not? We're doing astronomy. So this is from a kind of famous book for amateur astronomers, Norton's Star Atlas, which has lots of maps like this of basically all naked eye stars. And so you can actually see the historical magnitude system in operation in these modern day star maps. Okay, so here's stellar magnitudes, look, where bright stars are giving a bigger symbol, so magnitude 1 here, all the way down to the faintest naked eye stars, magnitude 6 here. Okay, and so this is exactly you know, the historical origins of the magnitude scale in action in a modern star map. And I'll just point out a few objects on here. I mean, I didn't choose this at random, so this is actually the relevant sort of star map for the portion of the sky that is pretty much overhead in the evenings at the moment. So there's a good reason why Vega was chosen as the standard star. It's very well placed in the northern hemisphere evening skies in the winter. And of course, the way the magnitude system works, you know, if you come across a new star, let's just, you know, one over here, for instance, you want to know its magnitude. All you do is point your telescope here and measure the flux. But then to calibrate it, you go and point your telescope at Vega to measure the flux. And then you've got the ratio of those fluxes. And because this is 0 magnitude, you can then work out the magnitude of this unknown star. Okay. So that's the idea, that this is your calibration point, and you reference every object back to Vega. Okay. If you want to find Vega in the night sky, it's quite easy. If you go out at the moment, probably if you're in the middle of Leeds, probably only these 3 stars you can actually see because there's so much light pollution around. So these 3 stars form, it's not a constellation, but it's referred to as the summer triangle. So sort of summer evenings, you'll see this triangle of bright stars, and that can orientate you, and Vega is this one here. Okay, and you might also spot this Cygnus, which is like the swan, or like a northern, also the Northern Cross, this pattern of stars. So it's quite easy to see. The green stuff up through here is the Milky Way. You'd definitely be hard pressed to see that in Leeds. You'd have to get outside and get onto a dark side to see that. We'll come back to the Milky Way later in the module. And if you're really interested in observing, then actually at the moment there's a bunch of shooting stars coming from the direction of Draco. The Draconids meteor shower is happening at the moment, but I tried looking last night. I didn't see a damn thing. A bit cloudy and a bit too much light pollution. Okay. So let's now move on to absolute brightness. So this is another consideration that we need to worry about, because so far we've just been talking about apparent brightness, so how bright an object appears to us here on the Earth looking up. Okay. Now, if you think about it for a moment, that might well have very little to do with how intrinsically powerful the object you're looking at actually is. Okay. And that's because of our old friend, the inverse square law for flux again. Okay. How bright an object appears to us here on the Earth depends not only on how intrinsically powerful it is, you know, how many joules per second of radiation, how many watts the star is pumping out. It also depends on its distance from the Earth, how far away it is. Okay. So, yeah, I'm introducing a bit of terminology here. You're going to have to bear with me here until we get to workshop 2 before you know what I'm really talking about. But we're going to introduce a new unit of distance. Obviously, the SI unit of distance is the meter. And in the sort of popular astronomy literature, you always see distances referred to in light years, the distance that light travels in a year. But we don't really use either of those in modern astrophysics. We use a unit called the parsec. So it's written like this. Actually stands for parallax arc second, which we'll cover all of this in workshop 2. So next week. Okay. So just bear with me that we're going to be measuring distances in parsecs, and that will be relevant for what we've got to talk about now. So just coming back to the question I posed at the beginning. Okay, so you know, an intrinsically very luminous star that is putting out a lot of radiation, but is a long way away, could appear very similar brightness to us here on the Earth as an intrinsically very, very faint star that just happens to be very near the Earth. Okay, and just by looking up in the night sky ain't going to tell you, and measuring the apparent brightness isn't going to tell you which case you've got. Okay, unless you know the distance. Okay. So I'm going to use this word intrinsic probably quite a lot in this module. So intrinsic means particular to that object. So an intrinsically luminous star is one with a high luminosity. Okay. An intrinsically faint one is one that's not got a high luminosity. So, we'd really like to know which stars are, genuinely bright and not just bright because they happen to be nearby. Okay. Which is a little bit the same as the difference between flux and luminosity. Okay. So for that, we introduce sort of a new concept on the magnitude system, which is called absolute magnitude. And here we do a kind of a concept experiment, if you like, where if we could move all the stars out there to be exactly the same distance from the Earth, okay, so you bring the far ones closer and push the near ones further out, they'd all be at the same distance from us, and therefore you could then say, oh yeah, that one's definitely much more powerful than this one over here. And so effectively that's what you do using this absolute magnitude scale. Now, of course, you can't really go out and move the stars around, but mathematically we can. Okay. So we define the absolute magnitude as the apparent magnitude that a star would have if it was at a distance of 10 of these parsecs. Okay, this unit of distance. Don't ask me why 10 was chosen. 1 would have been more sensible, but it is 10. Okay. So we're going to, in effect, move all stars to 10 parsecs and then compare their absolute magnitudes, which is the apparent magnitude they have at that distance. Okay. So it seems a bit arbitrary. It is a bit arbitrary. But again, it's, you see this time and time again when you look at lists of properties of different types of stars that we will see during the module. You will see lists of absolute magnitude, and that's the way it works. Okay, so let's try and derive a relationship between the apparent magnitude of a star and the absolute magnitude of a star. So effectively what we're doing here is trying to work out the flux that a star would have at this reference distance of 10 parsecs, big D as I'm calling it here, compared to the flux that it has at its actual distance, small d. Now, as we learned in the previous lecture, then flux varies with the inverse square law. Okay, so here you can see the inverse square law in action. You've got the distance, inverse distance squared here coming in. Okay, so all we need to do to work out the relationship between apparent magnitude, little m, so just be careful, especially if you're handwriting your notes here, to differentiate between little m, which is apparent magnitude, and capital M, which is absolute magnitude in this formula. Okay, so apparent minus absolute is, again, you just use Poisson's relation. Make sure we get these the right way up. Okay, so it'll be the flux of corresponding to this magnitude over the flux corresponding to that magnitude. And as we've just seen, we can substitute directly in the inverse square law now. Okay, so we're going to put big D and set it at 10 parsecs. And in this formula, we're going to have to measure D in parsecs. Okay. If we do that, then this formula then simplifies down to this. I've done a little trick with the mathematics here. Again, if you remember back to your sort of logarithms, if you've got a power in here, you can take that number out the front and multiply that one. So that 2 has disappeared, and the 2.5 has become 5. So that's 5 log D over 10. And we can simplify this a little bit more. Obviously, log of 10 is 1, but it's on the bottom, so it's negative, and it's multiplied by the 5 here. So this all becomes the definition of absolute magnitude, effectively. So little m minus big M is 5 log D minus 5. Okay. And just be careful, it's not log of D minus 5, it's 5 log D minus 5. Okay. And this is the first formula we'll come across. There aren't too many of these, but this is one of them, an important one, where things are not in SI units. So here, D has to be in parsecs, as you can see from the way it comes into the definition here. Okay. So in this case, to use this formula, D has to be in parsecs. Okay. But this is our definition of absolute magnitude, capital M. Okay. So again, let's put this into action straight away. So we'll give you a little example to do, just simple application of that formula. We'll take an example of a nice star again, that Betelgeuse, which is a lovely red star, very bright. So you can see its apparent magnitude. It's easily one of the very bright stars as well. Magnitude just over 0, so plus 0.5. And it's a distance of 220 parsecs away, okay, which is about 700 light years if you prefer light years, but this will do. Well, this is what you need for that formula, right? So I'm giving you the distance in parsecs. We'll worry about, definition of a parsec and how many meters are in it during workshop 2. Okay, so I'll leave you with that one to have a go at, and then we'll come back after the next break.